Hello everyone and welcome to the third video on the topic of RNN. So far in the previous two videos, we have discussed a lot of things like an RNN model is a sequential model which is good at working with sequential data like text, just like this sentence. And we also discussed that if we are feeding this sentence to the RNN model, that will happen in a specific manner. First of all the words individually will be converted into machine readable vectors. There could be multiple ways of converting texts into vectors, but for demonstration purpose, we are using a simple way over here. Okay. We also understood previously that since RNN is a sequential model, so the data as well will be fed to the model sequentially, which means for this particular single data point, which says he is tall. Since we are converting this data point into three individual vectors, therefore this data point will be fed to the RNN model in three different timestamps. That also in sequence, which means first of all we will feed this vector followed by this vector. We also discussed that when we are feeding one particular vector to the RNN model, then at this point, okay, the model will perform a feedback loop. It will send back itself some information that it has captured from the previous vector. Okay. And anyways, if you have covered the previous two videos, then you can precisely understand that what I'm trying to say here. This particular video, the third one in the topic of RNN, is going to be entirely based on forward and backward propagation. So we will understand that when we are feeding one particular data point to the RNN model, that also in sequence, one by one at a time, then how exactly the entire calculation or computation across the RNN circuit is actually happening. And then we will also understand that after computing the loss at this point, okay, how backward propagation is happening here in order to perform the optimization, or in simple words, in order to reduce this loss. Also within this deep learning playlist where we have previously covered ANNs and CNNs as well, I have already covered the topic of forward and backward propagation twice, once for ANNs and second time for CNN. So I'm going to assume that at least you have some basic idea that how this forward and backward propagation thing happens actually with ANN or CNN model. And if you were able to understand that part clearly, then obviously this particular video is also going to be very easy to understand for you, especially the optimization and derivative part. Because in this video, I'm not going to get into too much details of the mathematics. Otherwise, the length of the video will exceed too much. So let's get started, and we will start by understanding first that how and what exactly is happening in forward propagation. So here I am taking a simple representation of an RNN model. Okay. So these square boxes that you can see on your screen, these are actually representing this particular RNN model, this one. Okay. And by the way, just for demonstration purpose, I have kept only one input layer, one hidden layer and one output layer in this RNN model. But in practice, the number of layers or the number of perceptron on each and every layer could be anything. Okay. You can set the number to anything. All right. So let's move ahead. Next thing that I want to tell you is you can see three RNN circuits, right? But please keep in mind that these are actually the same RNN model. Okay, so this and this is actually the same and only one RNN model at different timestamps. Okay, so there should not be any confusion around this part at least. Now, for example, we are going to understand with the help of this data point that has only three words, which is he is tall. Okay. You already know that we feed this particular data to the RNN model in sequence, which means first of all, we will be passing this vector. Secondly, we will input this vector, and third or last, we will be inputting this vector. Okay. For the convenience of understanding, I am going to provide a naming convention here. So I will be calling this vector as x1. This will be called as x2 and this will be called as x3. I request for your attention here as we are going to discuss the entire operation of forward propagation from this point. Okay, so you know the first step. We are going to take the x1 vector and we will be feeding it at t1 timestamp to our RNN model at this point over here, x1. Now you can see the shape of x1. What is it? It is 1 by 5. So let me write it here. The shape of x1 is 1 by 5, which means only one row and 5 columns, and wi is going to be the weights at the input point. Okay, so let's try to understand in details that where and what exactly is this input weights. So let me show you the RNN model here, and let me make the screen a bit clear for you. So I will erase these things first. So this one is the x1 vector that we are feeding, right? And it is something like this: 1 0 0 0 and 0. This is what we are doing, right? On the first layer we have 5 perceptrons. On the hidden layer, or on the second layer, we have 3 perceptrons. And at this point we have the densed connection, or you can say the weights which are connecting these two layers. And you can see that here we have 15 weights. 5 multiplied by 3, we have 15 weights in total. And this is what we are calling the input weights. Okay, so you should be clear at this point at least that when I'm saying wi, I'm talking about all the weights at this point. Okay, so we are going to mention it here that wi has 15 weights that we will have to adjust during back propagation in order to minimize the loss. So I would rather write the shape of input weights here, which is going to be 5 by 3. Okay, and I will keep a note here that on wi we have 15 weights. I will also mention it here. So let me first erase all this and this, and I'm saying that wi has 15 weights. Okay, now back to the topic. So the next operation that happens during the forward propagation, a dot product between x1 and wi. Okay, so I'm going to mention it here, x1 dot wi. Okay, and the result of these two will come in a shape of 1 by 3. And you will be easily able to understand this if you have been following the mathematics playlist on my channel, where I have discussed in details that if the shape of the first vector is 1 by 5, okay, and the shape of your second vector is 5 by 3, in that case the dot product is possible if these two numbers are same, okay, and they cancel out each other, and the shape of the dot product will be 1 by 3. So in case you need more clarity around this kind of operations with vectors or matrices, or you want to understand tensors as a whole, I highly suggest you that I have a dedicated playlist which will work as a strong foundation for your machine learning as well. And over there you will find very simple tutorials around mathematics topic that you need to know when you are working with machine learning or deep learning. So you can consider checking it out. I will drop the link below. Anyways, so I will quickly erase this first, and let's try to understand that once we calculate the dot product between these two, then what happens next. This particular dot product will be then sent to a function. Okay, the dot product of x1 and wi, which means there will be a function exactly at this point where we pass the dot product of x1 and wi. And this function could be anything, but most of the time it is tan h. But as I said, you can change it to anything else. And when you pass the dot product to this function, this will give you this output O1 that you can see here. Okay, so I hope that you have a proper understanding that what exactly is happening on t1 timestamp. I'll start again. We take a vector of shape 1 by 5, which is x1, which is this vector, the first one. And then we have these weights, which is being denoted here by wi, that I have already shown you on the figure over here, which are these weights, okay, which are the connections between the input layer and hidden layer. So this particular vector is x1 dot, these weights are wi, so I'll say wi, and at this point you have the tan h function that takes this particular dot product and sends an output of O1 that you can see here, this particular output O1. Okay, so I'm assuming that you are clear what exactly is happening on t1 timestamp. If not, then you can consider watching it again. If yes, then let's move ahead. And now we are going to take this second vector, which is x2. So I'll write it here, x2, and again it comes in a shape of 1 by 5. And as discussed earlier, wi is going to have a shape of 5 by 3, obviously because it is the same model, just on a different timestamp. And this time again we do a dot product between these two, x2 and wi. Instead of writing x1 here, I will change it to x2 and wi. that will again give you an output of shape 1 by 3 that will be sent to the function of 10h, which is exactly over here. Okay, but at this point of time, we are not sending only the dot product to the function. Okay, in fact, previously we had some output from the previous vector x1, and that information is going to be sent back to the model on the next timestamp to this particular function. Okay, so there will be some changes with this function here. So let me do it quickly. Let me first take it and drag it over here, and this time it changes to x2 dot wi plus o1, which is the output that we have here at the previous timestamp, that will be coming through the connections of wh. Now this is something new that we have here. Okay, so let me mention that we have wh at this point. Now let's understand what is wh in the architecture of RNN. Okay, so let me erase very quick all of this. So previously we were working with x1 that was fed first to the model and gave us this output O1. Okay, now I'm going to erase this, and this time we are going to work with this particular vector, which is x2. So I will change it to 0 and this one will be changed to 1. So this one entirely is x2. So basically we are taking x2 and doing a dot product with wi, which is basically the weights and connection at this point of time. However, along with that, as we have studied earlier in the previous lecture, on this layer it sends itself a feedback loop, right? So along with the information of x2 or this second vector, it also sends back itself the information captured from the first vector, the information that it has stored in this O1. That information is being sent back over here via this route. And how exactly is that happening? So this particular perceptron will send the feedback to itself, to this perceptron, to this perceptron. This is 3. Okay. Secondly, this particular perceptron will send back the information to this one, itself, and the third one. And the same thing will be done by the third perceptron as well. So it is going to be a 3 by 3 weights. Okay. So when I'm saying wh, then it is nothing but, first of all, I will erase wi from here to make the screen more clear, and I will mention wi over here. Okay. And it is sending a feedback loop to itself, and we have wh over here. And this comes in a shape of 3 by 3. Or I should say in total it is going to have 9 weights. Now you might get confused that how exactly we have 9 weights over here, especially if you have missed the previous video. In that case, this particular confusion is very obvious. So I have a detailed figure on the top that I would like to show you. So this is the figure at timestamp t1. Okay, at this point of time we were able to calculate the output O1, and now this information which is stored on all these 3 perceptrons, 1, 2, 3. You can see these 3 perceptrons are sending the information forward to itself in the next timestamp to all the perceptrons on the same layer. And in simple words, I am talking about these weights. Okay, these weights. Even if you try to count, it has 9 weights. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So I'm talking about these weights only. So there should be no confusion around the weights at the hidden layer. Okay, so let's come back to the figure. So we have understood where exactly we have input weights and where exactly we have the hidden weights. So let me mention it here as well, that this information of O1 is coming through the connection of hidden weights that has a shape of 3 by 3. And now if you read this thing, it will make more sense to you. We are doing a dot product of x2 vector and wi, which is this one and this one. Additionally, we are also receiving the information from the previous timestamp that is coming in this shape, O1 and wh. And if you remember previously, we calculated O1 in this shape, 1 by 3, and wh has a shape of 3 by 3. So obviously you will be able to understand that what will be the shape of the dot product over here. Dot product of O1 and hidden weights. So it is going to be 1 by 3. Okay. And this is the second output that we have on the second timestamp. So again, I am assuming that you are clear at this point that what exactly is happening till timestamp 2. So let me erase all these and make the screen a bit clear for further explanation. So we have understood that how O2 is being calculated here. Okay. Now again, we move on to the next timestamp, which is T3. And on this timestamp, the RNN model will receive the information of vector x3, that is over here. Again, the shape is going to be same, 1 by 5. The weights on the input layer will have a shape of 5 by 3, since we have 5 perceptrons on the input layer and 3 perceptrons in the hidden layer. The information coming from timestamp 2 will come through the hidden weights, which has a shape of 3 by 3. Since we have already seen earlier, on the input layer we have 5 perceptrons like this, and on the hidden layer we have 3 perceptrons. And since the O2 has been calculated over here, O2 is right here, okay, when it is sending the information of O2 from T2 to timestamp T3, each individual perceptron will send forward the information to all the perceptrons on this particular layer, okay, and this is why it becomes a 3 by 3 weights. I'm trying to explain the same thing again and again because I really don't want you to get confused, okay. In case you are getting confused with the weights on the hidden layer, please take a screenshot of this particular figure and you will be able to understand that how exactly it is doing. We have the input weights over here, we have the input weights here, and then again here, and the shape of input weight is 5 by 3, or you can say you have 15 weights. Talking about the weights at hidden layer, we have one here and another one here, right here, okay. And I think I missed to draw the weights from this perceptron, so let me draw it quickly. So this is the first one, this is the second one, and this one is the third one going to the third perceptron, and the shape of WH is going to be 3 by 3 because all the 3 perceptrons in the hidden layer has a dense connection to itself in the next timestamp. Coming back to the topic, this time we are taking x3, okay, so let me change it to x3 over here, and we are doing a dot product of x3 and WI. The dot product will come in a shape of 1 by 3. So I will change this one as well to x3, and this time we need to change it to output 2, okay, since the output is coming from here. So this being in a shape of 1 by 3 and this being in a shape of again 1 by 3, adding these two, the output will be in shape of 1 by 3 only, okay. So this entire calculation is happening at this point. We have the function here. Now what do we do at the final step at this point when we have no more vectors to input to the model? So first of all, this calculation will give us O3, the output at this point, and this O3 is going to be multiplied with the weights at the output layer. So let me show you that where exactly is that. So we had the input weights here, the hidden weights here, okay, and the output weights is over here in a shape of 3 by 1. So this has a shape of 3 by 1. And this is why, since O3 is in a shape of 1 by 3 and weights on the output layer is in a shape of 3 by 1, the product of these two will come in a shape of 1 by 1, which means it will be a scalar value like XYZ, it could be anything, okay. And that information or that value will be then sent over to the sigmoid function. And after passing it to the sigmoid, the value that you finally get will be your y hat, which means your prediction against the real value or the actual value. And using this specific value, you calculate your loss. So in this case, so over here, the loss function which will be used, it will be binary cross entropy. So although you have come so far and after studying ANNs, CNNs, and now you are trying to understand RNNs, then you must be familiar with loss functions. But still, in case you need more clarity around binary cross entropy or any other type of loss function, then please consider checking out my loss function all-in-one video, where within one particular lecture I have covered all the important loss functions that you need to know. However, the point is that once we have calculated the loss, the journey of forward propagation ends here. And now our strategy around reducing this loss will be decided through the path of back propagation. So first of all, I am going to erase all this, okay. And by the way, I forgot to mention one thing, that when we were discussing about weights, okay, like WI or weights on the output layer or hidden layer, on each of these layers or for each of these perceptrons, there will be a bias as well, okay. So for example, on this hidden layer, the shape of bias is going to be 3 or 3 by 1, okay. And over here as well, you are going to have one bias. And therefore, when you are sending this information to the tanh formula or the tanh function, Then towards the end, you can also add or consider a bias term as well. So anyways, let me first quickly erase all this so that we can start the discussion around backpropagation now. So we have understood that how do we calculate y hat, and with the help of y hat, how do we calculate the loss? As a next step, all we try to do is to reduce this loss, and this is where the backpropagation starts. And prior to this, within this playlist of deep learning, we have already covered the topic of backpropagation 2 times. So it should not be difficult for you to understand that the idea of reducing the loss is around achieving the best values for all the weights within your neural network or your architecture of your model. So the first thing that we need to understand here is that how many weights exactly we have within the RNN model that we are trying to use here. So again, let's fall back to the detailed diagram here, and let me do some cleaning here first. Okay, done. So first of all, the weights that we have is weights on the input, weights on the hidden layer, and weights on the output layer. So Wi is exactly here. That is in a shape of 5 by 3. So we have in total 15 weights here. Okay. Now let's talk about the weights at the hidden layer, which means the weights at this point. So this will be in a shape of 3 by 3, as we have discussed earlier on this figure here. We are talking about these weights. These are 9 weights in total. Okay. So these are the second thing that we need to adjust. And finally, on the output layer, we have 3 more weights here. So it is going to be 3. Also, we have 3 bias over here, right here. Okay. So let's call it B1. So B1 is 3, comma. We also have B2, which is actually this bias over here. Okay. So it is only 1. So in total, we have 31 weights that we need to adjust. So what do we do? At this point, we use the concept of gradient descent. And as you know already, the formula of gradient descent says that if you want the new value of your weight, then you can use this particular formula. You take the previous value of the weight, okay, which is W old, minus a small learning rate multiplied by the derivative of loss with respect to the previous weight. So this is the part where the concept of chain rule comes into the picture in order to adjust the value of these weights on the input layer, on the hidden layer, these ones. Okay. You try to achieve the best values for all these weights that will result to the minimum loss. Or in simple words, I should say the prediction will start getting very closer to the actual values. And I have discussed the idea of chain rule within the previous 2 backpropagation videos within this particular playlist. But again, in this video, I will try to go ahead and show you how the chain rule is being applied in order to adjust the weights. I will do it for one weight, let's say Wi, okay. But the same concept will be applied for all the other weights on hidden layer or maybe in output layer or for the bias weights as well. So let's say that I want to adjust these weights on the input layer. Okay. So what will be the new value for these weights on the input layer? We already have the previous values and the learning rate value is being decided by us only. So this is the thing that we need to calculate, that how the loss can be controlled by bringing a small change on Wi, right? This is something that we need to calculate. So we start the chain rule from here. The loss is dependent on y hat. So we will say dl by dy hat multiplied by y hat is now dependent on O3. So we will say dy hat by dO3, and the calculation of O3 depends on these weights on the input layer. So I will say dO3 by dwi. So these will cancel out each other, and after calculating this, you finally achieve this particular value. And by the way, this was a very simplified version of the explanation. In practice, the backpropagation in RNN happens in a lot more complex way, and I will tell you why. Because adjusting the value for these weights is not going to be enough, because previously when we were adjusting the values for ANN or CNN model, that was fine because we were feeding the entire training data at a time to the model. Okay. At that time, the feeding was not happening sequentially. So the concept of timestamps was not there. But this time, if you are trying to adjust the value for weights on the input layer, first you will have to do it considering this timestamp T3. So you will have to apply the chain rule through this route, via this route. Okay. Then you will have to adjust the values for these weights on the second timestamp. Then again, you come from here and you go till this point. And the same thing will be done by coming from here and going till this point. But I really don't want to make this particular lecture mathematics heavy, okay? And there are two reasons for that. First of all, this entire thing of backpropagation and adjusting the values of your weights in order to reduce the loss is not going to happen manually by you. All these things will be executed with a simple line of code. But it is just that as a good data scientist or machine learning engineer, you should have some clarity around the operation happening behind your code execution. So when you're working with RNN, it should not look like a black box to you. And secondly, if you were able to understand the idea of backpropagation or optimization clearly in ANNs or CNN, then you can already understand that how the optimization is working here. By optimizing these weights and finding their derivatives, how exactly we minimize the loss. But still, in case you are curious to understand the calculation of these derivatives, which is happening by unfolding back to the timestamps, in that case, I will provide a link of a very helpful tutorial below in the description box. You can consider checking it out. But really, in order to work with RNN models, this much information should be enough for you. And there is one last important thing that I want to discuss with you before closing this particular lecture, which is around the limitations of RNN. The limitations due to which a need developed for more complex structures like LSTM and GRUs. So the thing is, over here, for simplicity purpose, in order to make you understand the entire operation of forward and backward propagation, I was considering a very small data point with only 3 words, which was he is tall. Okay, it had only 3 words. But in practice, a data point can have more words. In fact, it can have hundreds of words as well. In that case, you can understand that there will be hundreds of timestamps. This timestamp can go up to T100 or T150. And then, in order to minimize the loss, if you are doing the backpropagation and you are finding the derivatives for all of these weights, then by the time you reach to the starting of the chain, okay, let's say T0, at that time, the value of the derivatives will become so small that it will start causing issues like exploding gradients or vanishing gradients. And I will tell you that what happens due to this. Okay, so let's say, let me erase all this first. If I write a sentence like this, that I am from Nepal, and then I'm saying I speak, then a blank, and you are supposed to predict this particular word, then you can easily guess that most probably this language should be Nepali, or maybe any other language which is being spoken in Nepal. And it is because previously you were able to capture some information in order to predict this particular word, right? So over here, RNNs works fine in this specific case. But let's say that after the first sentence, let's say I'm saying that I am a BCom graduate and I am 20 years old. Then I'm saying I live with my parents, and then I'm saying that I speak, then a blank. So in a situation like this, RNN will struggle, okay, because the information that it had captured previously, okay, by the time it reaches to the end, it tends to forget this particular information. So in simplified words, RNN networks suffers with memory issue. They are not good with that. It is because when you are working with such a long text or document, then down to the chain where you have hundreds of timestamps, okay, the very initial derivatives at the initial timestamp will become so small, or the information will become negligible. It will have almost no contribution towards minimizing the loss or in order to predict the next word. And due to this limitation, or due to this particular reason, the developers felt the need of more complex models like LSTMs or GRUs. So basically, we wanted more complex architecture that should have the tendency of long-term memory. And let me tell you that the upcoming lecture is going to be based on LSTM and GRUs. These are relatively complex topics, but I will try to keep the explanation as simpler as possible, okay? Consider pressing the bell icon as well so that you can get notified as soon as I upload those tutorials. And also please subscribe to the channel if you are new here. I thank you very much for watching till the end. You have a nice day ahead.